Okay, so we have identified our oxidation, we've identified our reduction, we've been able to work through the oxidation and we're able to see what changes. To balance a redox reaction, you need three things: balanced elements, balanced electrons, and balanced charge. All right, those three right there. All right, in the simplest case, that is all you need to do. Balance the elements, undergoing redox, balance the electrons, balance the charge. So let's check. Let's try this. Okay, we take a look at this one. This one would be kind of balanced according to Chem 1 ideas. It's got one iron on this side, one iron on this side, one chromium, one chromium. All right, that would be awesome, except it's not done. Right? In a redox reaction, you also have to balance the electrons. Right? We can see that our iron, in this case, we have neutral iron plus chromium 3 goes to iron 3 plus a chromium 2. Right? So this reaction takes place. We can see that the iron goes from 0 to plus 3. That's our oxidation. Here's our reduction. So here's our oxidation. Here's our reduction. And we can write these out as half reactions, where we have iron going to Fe plus 3. That would result in a change of 3 electrons. And so that's our oxidation. And then we can talk about our reduction. And we can see that the chromium goes to chromium plus 2. That is a 1 electron change. And so therefore it's 1 electron. For this reaction to proceed, we would need to transfer 3 electrons. And so the way we do that is multiply this entire reaction by 3. And so this would be Fe plus 3 Cr plus 3s goes to Fe plus 3 plus 3 Cr plus 2s. The 3 electrons that are here cancel out the 3 electrons that are here. If we add these two reactions together, Hess's law style, add those two reactions together, and you should get a balanced reaction. This electrons and this electrons cancel one another out. The 3 that are on the starting material side cancel out the 3 that are on the reductant side. Now, product side. I will say, though, that it's important to remember this number. 3 electrons exchanged in this case. So that is balanced all of our elements, balanced our electrons, and now we look through the system and decide whether or not it is done. And the easiest check, besides the elements and the electrons, is the charge. Here we have plus 9, here we have plus 6, here we have plus 3, so the charge on each side is plus 9. That's going to be balanced out by some counter ion. That is the process. That's the simple process. So things get a little crazier, though, when there are other elements involved. So in this case, we have an iron becoming an iron plus 3. This chromium 6 becomes a chromium 3. This is being oxidized. This is being reduced. All right? So these are present. But there's a whole bunch of oxygens here that need to be managed. And so oftentimes we do oxidation and reduction chemistry in the presence of acid or base in water. So there's lots of water, there's lots of extra H+, there's lots of extra OH- that can do things for us. And so that's the implied knowledge, that this information is there. So we're going to use that. We're going to take a look at this reaction, and we're going to go through those same processes, balance the elements, balance the electrons, balance the charge. And the way we're going to do that is by modifying the procedure. Now, there are multiple ways to do this. If you go online and search balanced redox reactions, it can get weird. I'm going to show you one way. And that's the way I want you to use because it's convenient. What we're going to do is we're going to start under acidic conditions, regardless of whether it's acidic or basic. Balance it under acidic conditions because the process is simple. You balance the element undergoing oxidation or reduction. If there's two atoms, you need to make sure that there's two atoms on each side of the equation. Start there. Then you balance the electrons by modifying the coefficients like we saw. And then you balance the oxygens by adding water. And you balance the hydrogens by adding H+. We'll go through it. All right, so let's take a look. All right, so we identified our half reactions, and so we have our oxidation. It's going to be the Fe+2 going to Fe+3 plus 1 electron. We have our chromate as our reduction. This is the Cr2O7 minus 2. Going to Cr+3. And the temptation is to say, oh, that's a 3 electron reduction. But the first step, step 1, balance what is undergoing redox. The element that's undergoing redox, there are 2 of them here. That means there are 2 of them here. Now, what we see then, this goes from +6 and +6 to +3 and +3. This is a 6 electron reduction. So we can see that that's a 6 electron reduction. Once we know that, then we can then balance the electrons. So step 1, balance the element undergoing redox. Step 2, balance the electrons. There's 6 being transferred here. There has to be 6 here. So we'll multiply this entire thing by 6. And at this point, I like to combine the two. Your book may do it differently. You may see it done differently. I like to combine the two. 6 Fe+2 plus Cr2O7 minus 2 goes to Fe+3 times 6 plus 2 Cr+3. So if this was, again, if we were looking at our last example, this would be done. We have balanced the elements, we've been balanced the electrons, but you can see that the charge is all wrong. The charges are all wrong on each side. Additionally, there's these extra oxygens. All right? So, under acidic conditions, once you've balanced your elements, once you've balanced your electrons, the next step is balancing extra oxygen by adding water to the opposite side. So the oxygens are here, those oxygens are not here, and so we add waters. We have 7 oxygens here, we're going to add 7 H2O. All right. Remember, this is in water. These are in water, and the acid is going to actually cause the oxygens to be bound up and spit them off as water molecules. So we've added 7 waters to this side. And now we're balanced our oxygen, 7 and 7. That's awesome. So now we can then take another step and say, okay, what's now wrong with all these extra H pluses? So now we can balance the H pluses by adding H plus to the side that's deficient. So in this case, there are 14 H pluses missing. So now, if we finish this up, we'll have 14 H plus 6 Fe+2 plus Cr2O7 minus 2 goes to 6 Fe plus 3 plus 2 Cr plus 3 plus 7 H2O. And it is balanced with respect to all the elements present. Notice here the charge is 14 and 12, 26, 24, and 18, and 6 is 24. So it's plus 24 on this side and plus 24 on that side. Now, those extra plus 24 are going to be countered by ions like potassium or sodium or some other crap that's floating in solution. But they're spectators, and so we can ignore them. So this would represent the balanced chemical reaction. This is important for two reasons. We know that it's a 6-electron process, and this reaction has concentration relationships in form of an equilibrium. So we could write an equilibrium constant statement for it, or a Q for it. Very important. Because now when we know the balanced reaction, these are easy. And we can see that this H plus is going to be in the denominator. It's going to have a huge power relationship. All right? And so there's going to be some very high sensitivities to the spontaneity of this reaction depending on acid concentrations. So let's take a look at another example, but under basic conditions. Under basic conditions, it is exactly the same as under acidic conditions, except one small change at the end. All right? So we identify what's undergoing oxidation, what's undergoing reduction. And so in this case, we can see that the copper is being oxidized, the nitrogen is being reduced, and so we can see that the copper goes to copper plus 2 electrons. That's our oxidation. Our reduction, on the other hand, is the HNO3, forming NO. It's one nitrogen, one nitrogen. This is a 3-electron reduction. This is plus 5, this is a plus 2, 3 electrons. We then find the least common denominator, so we multiply this one by 3, and we can multiply this one by 2, and so we get 3 coppers plus 2 HNO3s goes to 2 NOs plus 3 Cu plus 2s. And I'm dropping out the electrons, 6 electrons and 6 electrons, I'm dropping them out. All right, so that's balanced with respect to the elements, that's balanced with respect to the electrons, and now we go back and we balance the oxygens by adding water. Again, just like under acidic conditions. So here we have 6 oxygens, here we have 2, so we're going to need 4 waters. So we have 6 and 2 and 4, so there we go. Now we have 6 waters, 6 oxygens on each side. Now we balance those, and now we balance the hydrogens. We have 2 here already, so we need to balance those 8, so that'll take us 6 H pluses. Now, if that was under acidic conditions, we'd be done. If it was under acidic conditions, we'd be done because we wouldn't have to worry about it. But notice also what we did. We worked on one side, and then we worked on the other. We worked on one side, and then we worked on the other. But with hydroxide, when you balance under basic conditions, you're assuming everything is in base. And so what you're going to need to do is add hydroxide to both sides. And you're going to add enough hydroxide to both sides to cancel out all the extra H+, because it's basic. Solution's basic. And so you're going to add 6 H pluses on this side, 6 hydroxides on this side, and 6 hydroxides on this side to balance out those. These will cancel out. Okay? And when you add H plus to OH minus, that makes 6 waters. But those 6 waters are counteracted by some of the waters here, and so overall the reaction would be 2H2O plus 3 copper plus 2 HNO3s goes to 2 NO plus 6 OH minus plus 3 Cu plus 2s. We check our charge, -6, +6, total charge is 0, total charge is 0. Done. The reaction is balanced. Now it seems a little bit crazy to do it like that, but it turns out that it works, and then that way you only have to memorize one way to balance both of them. There are alternate ways. You'll look online, you'll find 2 or 3 different ways to balance acidic and oxidation on basic conditions, but this allows you to do it with one. Balance the element, balance the electrons, balance the oxygens by adding water, balance the hydrogens by adding H+, check the charge. Okay? It's that simple. Okay? Now, what's nice about these half reactions, copper going to copper +2 and HNO3 and going to NO3, those half reactions are just chemical reactions. And it turns out that those half reactions do not need to happen physically in the same location for this reaction to still meet the second law of thermodynamics, or in other words, for it to proceed. Right? And so that is why batteries work. We're going to talk about that next.